Hi, this is Vinci Sharika of Artificial Intelligence and Data Science. The topic we'll be discussing right now is hidden Markov models implementation, which is thereby our fourth experiment. So, moving on into the aim or the overview of it, this experiment is all about the implementation which is used to predict the hidden state sequences from observed data using hidden Markov models. And the places it is used, or speaking about its use case, it is used in model weather states such as sunny or rainy based on the mood observations, happy or sad or whatever mood you are. And the method which we are going to use over here is the forward algorithm with alpha matrix computation for probability calculation. So before going on into the implementation parts, let's first try to understand what is a hidden Markov model. So the framework of the hidden Markov model, which is also known as HMM, is used to reveal the invisible states through observable patterns. In our weather example, we can't directly observe sunny or rainy states, but we can observe the moods. So the key insight which we have to take over here is that the model uses probability matrices to connect what we see, which is the observations, whether it is sunny or rainy, to what we can't see, which is the hidden states over there. Moving on into the core components of our HMM, the first one is the transition matrix. It defines the probabilities of moving between hidden states. The state can move from sunny to rainy, or the state can move from rainy to sunny, or staying in the same state. The second one is the emission matrix. It specifies the likelihood of each observation given a hidden state. For example, probability of being happy when it's sunny, or probability of being sad when it's rainy, or so it depends upon the mood we are and the observation which we observe. And the initial probabilities are starting probabilities for each possible hidden state at the beginning of the sequence. And the observed sequence is nothing but the actual data we collect, which is the mood observations that we'll see to infer weather states. Uh, the first process within this HMM is the forward algorithm process. The forward algorithm efficiently computes state probabilities by building an alpha matrix that tracks the probability of being in each hidden state at each time step. This dynamic programming approach avoids redundant calculations by using previous results. It uses the previous results for the next set of computations. And the algorithm implementation steps are as follows, as we discussed earlier. It starts by initializing the alpha matrix. Here we just create a matrix with zeros, and the rows is nothing, the number of rows is equal to the time steps we use, and the columns are the hidden states over there. And what we do next is to calculate the first row. We multiply initial probabilities by emission probabilities for first observation. And then we forward the pass loop. For each subsequent observation, we compute the probabilities using previous alpha values and the transition matrix. And the next step is to extract the results, which is where we sum the final row for total probability, and we select the highest probability state at each step for most likely sequence. And then moving on into the actual implementation, so we use Python over here. At first, we import the NumPy library, which is used for the mathematical calculation, as we use matrices over here. So moving on into the code structure, the implementation uses NumPy for efficient matrix operations, and the arrays represent state transitions, emissions, and observed data. Observation encoding, we have encoded 0, which is sad, and 1 as happy over here. And then we're going to first define the model parameters, which is the transition matrix over here. At first, we are creating an array with 2 rows and 2 columns. So for 0 0.1, 0 0.3, 0 0.4, and 0 0.6. Looking on to this, while we add up the rows, it should be 1. The sum of the elements in the rows should be 1, and then we create an emission matrix same as that. And then we initialize the probabilities. We are using zero point 0.5 and zero point 0.5, okay, and the observed sequence as 1110011, which says that for the first three observation we have noted that the observation is happy, as we have encoded happy as 1, and there are two zeros, which implies that the mood or the observation implies sad over there. And then we initialize the alpha matrix, where alpha is equal to np dot 0, as we have seen earlier over here. We create a matrix with zeros. That's what we are doing over here. We are creating a matrix with zeros with the length of observed sequence, which is this, and the length of initial probability is over here. Moving on into the forward algorithm computation. At first step, we initialize the alpha and the observed matrix over here. And moving on into the recursive calculation for the remaining steps. For t in range 1, until the length of the observed sequence, we iterate this loop. And within this loop, we have defined another loop over there. And upon all these calculation, after all this calculation, we'll be able to calculate the total probability, which is nothing but the np dot sum of alpha minus 1, which is nothing but it sums up the elements in the alpha. And then we are about to find the most likely state sequence. So we have defined an empty array for that, and again we are defining a loop to iterate through it to find which is the most likely sequence to be added, whether it is sunny or rainy. We have defined that if the alpha value is greater than alpha, if the future or the zero is greater than 1, the value where 0 it is, if it's greater than 1 or whatever it is, we would imply that the most likely sequence would be sunny over there. So after all these execution, the output would be for the matrix we have defined over here. For these set of values, we get this as an output. So the probability is 0.03628. This represents the likelihood of observing the sequence happy, 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 sad, sad, happy, which is given our model parameters, and the state sequences. The model predicts the weather pattern that most likely produced the observed moods. The thing which they have done over here is nothing but the thing which we have defined over here, the observed sequence. This is what they mean as we have encoded it into zeros and ones. So that's it. Looking on into the real world applications of HMM models, we use HMM in speech recognition, which is where it is used to identifying phenomena and words from audio signals by modeling hidden linguistic states, and bioinformatics, gene prediction and protein structure analysis through sequence pattern recognition, financial modeling, market regime detection and algorithmic trading based on hidden economic states, natural language processing, a part of speech tagging and named entity recognition, and text processing pipelines. So the result of whatever we've done so far is we have successfully implemented the HMM model using Python for state sequence prediction. Thank you. Hi, this is Vinci Shavita of Artificial Intelligence and Data Science. The topic we'll be discussing right now is hidden Markov models implementation, which is thereby our fourth experiment. So